Hello everyone, I'm Nikolai Priezhev, and this is a short presentation on eigenvalues and eigenvectors. This is an important concept in the analysis of linear transformations and solution of linear dynamical systems. In this presentation, we first introduce the concept, then provide geometrical interpretation, and consider a couple of examples on how to find eigenvalues and eigenvectors for simple cases, followed by short conclusions. Good, so let's start then with introduction and consider matrix A to be an n by n matrix, and then a scalar lambda will be called an eigenvalue of matrix A if there's a non-zero vector x. We call it eigenvector such that the following equation will hold true. So here A multiplied by vector x is equal to x itself multiplied by a scalar that is eigenvalue. So in other words, the matrix A effectively stretches the eigenvector by an amount specified by eigenvalue lambda. Good, so one comment here is this requirement of non-zero vector x is important because trivial solution x is equal to 0 will satisfy this equation for any value of a scalar lambda. Good. So one historical remark that goes with it. This terms eigenvalue and eigenvectors are hybrid German English words. Okay, and in the original German, they are pronounced like eigenwert and eigenvector, which can be literally translated as a proper value and proper vector. Good. Okay, so let's discuss briefly a geometrical interpretation of eigenvalues and eigenvectors. And for simplicity, let's consider a two-dimensional case where vector x is plotted in the xy plane. Now, a linear transformation defined by the following matrix will result in a new vector, which is A multiplied by x. And this vector is rotated with respect to x, and its length is changed. Okay. Now, by contrast, we will learn that it's possible to find such a matrix A. So then linear transformation AX vector will be oriented parallel to x. Okay, and its length will be modified by a scalar lambda, which is an eigenvalue. So in other words, okay, we can say that eigenvectors specify the direction of so-called pure stretch for linear transformation defined by matrix A. Good. So let's consider the following example and see how our equation works in case of a two-dimensional matrix A. Okay, when eigenvectors are known 1, 1 and 2, minus 1. Good, so then let's consider the first one. So it will be a product of A multiplied by x1. Okay, we'll write down our matrix multiplied by 1, 1 and compute the resulting vector. Okay, what will be the result here? 1 plus 4 is equal to 5. Okay, now 2, okay, plus 3 is equal to 5 again. And we notice that this vector is equal to 5 multiplied by 1 by 1, 1. And this will be our original eigenvector. So therefore, the prefactor before this vector will be an eigenvalue 5, right? Good, next one. So A now multiplied by x2, the same matrix, multiplied by 2 minus 1, and this will be equal to what? 1, okay, multiplied by 2, okay, minus 4 minus 2. Then 2 by 2, 4, minus 3 is equal to 1. One can further notice that if we multiply this vector by -1, okay, then we arrive then to our original eigenvector. So therefore, the factor -1 will be our eigenvalue. Good. So notice then for this matrix, the eigenvectors were known, okay, but in general, we would need to find both eigenvectors and eigenvalues. So let's see how to do this, okay, in practice. Well, let's start then by rewriting our definition in the following form. Lambda multiplied by I, which is identity matrix, okay, with 1 on the main diagonal and zeros everywhere else, multiplied by x. Okay. Putting this on the left-hand side, rearranging, we have an equation where the term here in the brackets is we call it characteristic matrix. Now, in this equation, remember, we are looking for a non-zero, non-trivial solution. X is not equal to 0, so meaning the determinant of this matrix has to be equal to 0. So in other words, then, a scalar lambda is will be an eigenvalue of matrix A if and only if lambda is a solution of the characteristic equation, determinant is equal to 0. Okay. Good. So more specifically, let's consider the system of linear equations written down in a matrix form where Aij here are the elements of matrix A, and we subtract lambda along the diagonal elements of this matrix. Good. Multiplied by x, and this is equal to 0. Okay. Now, then determinant of this matrix is equal to 0, characteristic equation, and we can then rewrite this as the nth order polynomial equation as follows, equal to 0, and in general, this equation would have n roots. Okay, so those roots are the eigenvalues of the matrix A. Okay. Now, once we found this eigenvalues, then we go back to our eigenvalue equation, plug this in, and go ahead and find corresponding eigenvectors. Let's see how we can do this in practice. Okay, so consider, for simplicity, then 2 by 2 matrix, and try to compute the determinant in the characteristic equation. So A minus lambda I is equal to what? So same matrix, minus lambda minus lambda. Open it up and we get a quadratic equation. Okay, so this is equal to 0. It gives us characteristic equation. And then we can further factor this out in two terms. Lambda minus 4, lambda minus 2 gives 2 roots, 4 and 2. So we conclude here that matrix A has two eigenvalues. Lambda 1 is equal to 4 and lambda 2 is equal to 2. Okay. Good. Next step. How do we find characteristic eigenvectors? So we then use this equation and find these two vectors. Let's see how it works. Now the first eigenvalue, lambda 1 is equal to 4. Okay, and we write our characteristic matrix then as follows. So A minus 4 multiplied by 2 by 2 identity matrix, okay, is equal to what? So 3, okay, minus 4 minus 1, 1, 1, and this minus 1 multiplied by zy, this is our eigenvector, is equal to 0. So let's rewrite this as a system of linear equations. How do we do this? So minus 1 multiplied by z plus 1 multiplied by y, first equation. Second one. So 1z, okay, minus 1y is equal to 0, second equation. Now let's look at this. One can notice that actually those are the same equations up to a factor of minus 1, okay, and therefore the general solution of these equations then will be z is equal to y and is equal to a, where a is an arbitrary scalar except for the case is equal to a is equal to 0, this trivial solution. Good. Okay, so we write then our answer as follows. So it will be a vector with the components a and a, or we write that this is a multiplied by vector 1 and 1. So what follows then, we call this is our eigenvector, where we keep in mind that any scalar multiplied by a will also be an eigenvalue of matrix A for this eigenvector. Good. Second case, lambda 2 is equal to 2. Okay, so in this case, our characteristic matrix will be equal to A minus 2i. And we write this as follows. So remember, so A 3, okay, minus 2, 1, 1, 1, and 1. So all the unit matrix multiplied zy is equal to 0. Good, so by inspection, it's clear that any vector of the form A minus 1, 1, okay, T stands for transpose, will be a solution of this system of linear equations. So therefore, okay, we conclude that our solution for this problem will be eigenvalue 1 is equal to 4, and the corresponding eigenvector is 1, 1. And eigenvalue 2 and eigenvector will be minus 1 and 1. So note as a comment that those are linearly independent vectors. Good. So let's summarize what we've learned today. We introduced the concept of eigenvalues and eigenvectors using the following equation. Okay, so in a sense, then matrix A effectively stretches vector x by lambda, but it doesn't change its orientation. Good, and our solution to this problem goes as follows. So we have our equation then rewritten then in the following form: lambda multiplied identity matrix multiplied by x. Okay, and rearranging, we introduce so-called characteristic matrix. Now, for a non-trivial solution that boils down then that this matrix, determinant of this matrix, have to be equal to 0, and this gives us so-called characteristic equations. So determinant A minus lambda is equal to 0, and this in turn can be formulated as nth order polynomial in lambda, which can be solved to get n roots. Okay, and so those roots will be our eigenvalues for matrix A. Once we know these eigenvalues, we can plug this in our characteristic matrix, okay, and solve for corresponding eigenvectors. Good. Well, hope it helps in solving some problems. Okay. Would like